Okay, so part 3 of this look at trying to find the comparing samples to means. Here's an example where we compare the mean. We're trying to test the average price of an automobile that was sold on a used car lot, and the mean under the null hypothesis is 14,050. Now the level of significance on this, we set it at 10% because if we're wrong, it's not going to be life or death, and we could definitely be wrong to the point of 1 out of 10 times to give ourselves like a wider target, basically. Remember my example I gave you. If you ask me within 1% certainty what time we're going to eat Easter dinner or Thanksgiving dinner, and I tell you it's 3 o'clock is the invitation, but if you want 1% certainty, then I'm going to tell you anywhere from 2:45 to 3:15. But if you're willing to live with 10% certainty, then I can give you a tighter number, maybe 5 to 3 to 5 after 3, because you're giving me more room for error. So I could be tighter with the idea that we both understand that there's more room for error. That's probably the best way to explain it to a layman. But so here we set a 10% significance. You could set a 1% significance if you have something that's more, like say for instance, something that really is crucial, where you're going to make a financial decision or a health decision. If you're testing, say, a vaccine, you may want to make it 1/10 or 1,000th of 1%. So at any rate, put this mean in. We have a lot of samples, and that's another point I want to make, and I made it in previous videos. More samples, or large numbers, you're going to have a smaller standard error, because basically you're dividing over a bigger number. That statistic will allow you to divide over a bigger number. So more samples will allow you to have a smaller standard error. Less samples, you obviously would use a student's t-distribution, you'd have a larger standard error. So these are the numbers that the claim is at. That's the null hypothesis, that's the claim. The claim is the average car on our used car lot sells at 14,050, and we're going to use a 10% significance. We take a number of samples, 500 in this case, and we come up with 500 cars that actually sold at 13,795, which is not too far off, but the standard deviation is 2875. And in this case, we're going to use a z-distribution since we have so many samples. So, and we want to know that, is that at least, oh no, we're going to use a two-tailed distribution. Of course, we're making a very specific claim. So two-tailed, we're going to need a standard deviation or a test statistic that's unique enough that comes within minus or plus 1.64 standard deviations. And if you recall your z-tables, that's about 1.64 standard deviations is approximately 5% probability, but since it's two-tailed, we got 10% probability, and that equals your level of significance. So your tested statistic is minus 1.98, and that's going to get us at 0.04, which is well below the 10%. So the claim is actually correct. It's close enough to make that claim. Now notice if I lower this to 0.05, what happens here? Let's take a look. Okay, my test statistic stays the same, and I'm still close. Right? What happens if I go to 0.01? Well, now my two-tailed test is 2.57 standard deviations. My test is actually 1.98. Now I'm not going to make it, right? My two-sided p-value is going to be 4.7%. I'm looking for a level of significance of 1%. Basically, if I look at a normal distribution, I'm not coming within the 1%. I'm outside of it by 4.7%. But I'm only going to be wrong 1 out of 100 times. Whereas if I set it at 10%, my original supposition, I can afford to be wrong 10 out of 100 times, and I can go ahead with the understanding by all parties that there's a 10% level of significance, that I could be wrong 1 out of 10 times, that the 14,050 claim is, I will not reject the null, and I'll accept that as a valid claim. And that kind of gets us, I may do one more on t-distribution, but that kind of gets us to where we need to be on this. Thank you.